Ever stop and think about what it really takes to create the tiny brain inside all of our electronics? Well, today, we're going to pull back the curtain on one of the most complex processes on the planet, making a custom microchip, or an ASIC. And we're going to follow that entire journey from a simple idea all the way to a finished piece of silicon, using a basic calculator chip as our guide.
Right? It's something we take for granted, but that tiny little black square is the result of an absolutely epic journey. A journey that doesn't start with silicon or fancy labs, but with a simple question. What do we need this thing to do? From that one question, it becomes a marathon of design, translation, and microscopic construction.
So, we're going to break this whole adventure down into 4 main parts. First up, how we turn a basic idea into a digital blueprint. Then, we'll see how that blueprint, which is written in code, becomes an actual circuit diagram. After that, we get to the fun part, physically designing the layout of that circuit. And finally, the grand finale, manufacturing the real thing.
Okay, let's dive into phase 1. This is all about defining the mission. Before a single wire is even imagined, engineers spend a massive amount of time just figuring out and documenting exactly what this chip needs to do.
This first stage breaks down into 4 really important steps. First, you need a super detailed specification. That's the goal. Second, you create a high-level architecture, kind of like drawing a map of the whole system. Third, designers get to work writing the code that describes how the chip behaves. That's the RTL design. And finally, maybe the most important step of all is verification, where they test that code like crazy to make sure it's perfect. Everything, and I mean everything, starts with this document. It's the rulebook for the whole project. The customer spells out exactly what they need. So for our calculator, you can see it has to do the basic math operations, it needs to control an 8-digit display, and it has some really strict rules, right? Like a specific power budget and a set clock speed. Every single decision from here on out is governed by this document.
Now, this is where it gets kind of wild. A physical chip actually begins its life as pure code. Yeah, you heard that right. Using a special language like Verilog, engineers describe all the different parts of the chip. So for example, they'll write the code for the arithmetic logic unit, or ALU. That's the bit that actually does the math. Then they run this code in a simulation to make sure it works exactly as the rulebook demands, long before any real hardware exists.
So, we've got our code, it's been tested to death in a simulation. What's next? Well, let's move on to our next section, because this is where that abstract code starts turning into something that we can actually build. This is where the digital world starts to meet the physical world.
This bit of magic happens in a step called synthesis. You can think of it like an expert translator. This powerful software takes the code, which describes what the chip should do, and converts it into what's called a gate-level netlist. This is basically a super detailed instruction manual listing all the basic electronic components, or logic gates, and showing exactly how they need to be wired together. It's the how that makes the what a reality.
And what's really fascinating is that the exact same code can produce totally different chips depending on the manufacturing technology you're aiming for. So if you target an older 180 nanometer process, you get a chip that's bigger, slower, but really good on power. But if you take that same code and target a modern 10 nanometer process, you get a tiny, incredibly fast chip, but one that comes with a whole new set of complex design challenges.
Now, before we go any further, the engineers add something really clever called design for test circuits. Imagine building a car engine, but then sealing it completely shut. How would you ever know if a piston was bad? Well, DFT is like adding special test ports into the chip. These circuits allow automated equipment to check every single internal component of the finished product to make sure there aren't any manufacturing mistakes.
And the last major checkpoint in this phase is static timing analysis. This is a crucial check to make sure the chip can actually run as fast as it's supposed to. The software calculates how long it takes for signals to travel through all the different paths in the circuit, confirming it can meet that 100 kHz heartbeat we need for our calculator. If it's too slow here, it's back to the drawing board.
Okay, now we get to the really visual part, physical design. At this point, we have a verified list of millions of components and all their connections. The goal now? To lay all of them out perfectly on a tiny piece of silicon. The best way to think about it is like designing a microscopic city.
And just like building a city, the first step is zoning. It's called floor planning. The designers decide where all the major districts or functional blocks are going to live. So for our calculator, they'd probably place the ALU, the brains of the operation, right in the center, with its memory right next door for quick access. And then the input and output pads that connect to the outside world get arranged around the edge of the chip.
Next up, you have to build the city's public transit system, the clock network. A process called clock tree synthesis creates this perfectly balanced delivery network. Its only job is to get the chip's 100 kilohertz heartbeat signal to every single component at the exact same time. Any delay, or what's called skew, could cause the whole chip to mess up.
And now, with all the buildings in place, it's time to build the roads. This is routing. It's this incredibly complex, automated process where software lays down millions of microscopic metal wires, often on many different layers, to connect every single gate and block, exactly like the plan said. This is what finally turns a collection of parts into a working circuit.
But before this city plan can be sent off to the factory, it has to pass a final, super strict set of inspections called sign-off. Automated tools run the ultimate fact check. For instance, a design rule check, or DRC, makes sure no wires are too close together. And another check called layout versus schematic, LVS, confirms that the physical layout is a perfect one-to-one match of the original circuit diagram. Only when every single rule is passed does the design get the green light. And that brings us to our final section. The design is done. It's been checked, double-checked, and triple-checked. Now it's time to make that incredible leap from a digital file on a computer to a physical object you can actually hold in your hand.
These last few steps happen in pretty quick succession. First is tape-out, when the design is finalized and sent to the factory. Then comes fabrication, that incredible process of actually building the chip on a silicon wafer. After that, the chip is cut out and put into a protective package. And finally, it goes through intense testing, using those special circuits we added earlier to make sure it all works perfectly.
Tape out is the big one. It is the ultimate point of no return. This is the moment the design team literally hits send on the final design file. This massive file, called a GDSI2, contains the geometric blueprint for every single layer of the chip, and it gets sent to a foundry. Once it's sent, that's it. There are no do-overs. A single mistake here means starting the whole physical design all over again, a mistake that could cost millions of dollars and months of work. And there you have it, the complete journey. We started with nothing but an idea. That idea became a detailed specification. That spec was turned into code, which was then synthesized into a circuit diagram. That diagram was laid out as a physical city on silicon, and finally, that city was built, packaged, and tested. It's just an amazing combination of human creativity, powerful software, and pure physics. So, the next time you pick up your phone or use your computer, just take a second to think about the journey of the silicon inside. We just walked through the process for a simple chip that maybe has a few thousand transistors. The processor in your phone has billions. It's the same fundamental journey we saw today, just scaled up to a level of complexity that is truly, truly mind-boggling.